Hey Kevin, how are you? Okay, so we'll start shortly. Sorry for the late post. If you can go into Canvas and check out the notes and the assignment, pretty easy today actually, even though there are like 3 chapters. Maybe they'll pop in a minute. Okay, I'm gonna go ahead and share screen real quick. Just you and I right now, so. Huh. Sorry, I just, 1 second. It's not. Oh, what is going on with Zoom? Okay, sorry about that. I had something is happening with my bandwidth and it's causing me to. Okay, so let's take a look at your notes. I was trying to squeeze the other chapters in, but I think we're probably just gonna hit the 3 things and then we're gonna do the lab with Gil, which we've seen with the prior chapters before. So we're going to talk about deadlock, starvations, and race conditions today. This is, so in your textbook, the following chapter after chapter 13 is just the review, and it talks about concurrent programming and parallel processing, giving you some example with multiprocessing module being used, which we've seen from the prior chapter. So in the lab, we are going to hit the global interpreter lock, which is what we've seen being used in the prior chapter when we talked about multiprocessors. So for now, we are going to go over 19, 20, and 21, which address deadlocks, starvations, and race conditions. And we talk about how to be able to work around those type of issues. Okay, so and they are fairly short chapters. They're not as lengthy as the other ones, so we can basically hit 3 to 4 chapters this week. My plan for next week is to go over patterns, and that would wrap up all the concept that we need to cover as far as the course objectives. Then we will do the final review in week 14. And then that will give you week 15 to prepare for your final exam and your project. And then you will need to take the final exam in week 16 and to be able to submit your project as well. Okay. So this week we are going to cover deadlock in chapter 19. And these are some of the common problems that you would see with concurrent programming. And so we would need to take a look at what caused the deadlock and how to work around the deadlock. So a deadlock is when there is no progress made in the program. It is usually caused by mishandling the lock objects in synchronization of the thread or processes. So in the prior chapter, we touched on how to use parallel processing, and also after that, we talked about how to use multi-threads. So the book gives you the example of 5 philosophers, 5 people sitting around the table, and in order to eat, they're gonna need 2 forks. And so now there's a left fork and there's a right fork, and each of the philosopher needs to pick up both forks in order to eat. And they would alternate between thinking and eating. Now, in order for one philosopher to be able to eat, they would need to pick up the left fork and then put it down, and then pick up the right fork and then put it down. And so as they release the forks, the adjacent or the neighbor philosophers would be able to eat. And so that's what we would see in a sequential program, in that the functions would then release the CPU, and that CPU would then be able to have to be able to be used for the subsequent functions. But what happens when all the left forks are picked up at the same time? Then no one is still eating, because then you have to be able to pick up the right forks in order to eat. So here what it's saying is that when the philosopher pick up the left fork, they need to also use the right fork in order to pick up the food. Now, when they're holding 2 forks for a certain amount of time to eat a certain amount of food, then when they return the left and right fork, then subsequently there will be progress. But if the forks are not returned to the table, then there would not be any kind of eating or progress in the program. So this is just an example on how it would be using forks to eat with philosopher. Now, if all of them pick up the left forks, then none of the left forks would be available for other philosophers. If the philosopher is not eaten, then they won't be able to release the forks as they're holding it. And so as each of the philosophers is holding the fork with their left hand, they cannot proceed to eat, therefore they cannot put down the fork. So it is a catch-22 in that we cannot eat without the fork, and we cannot release the fork until we eat, and we cannot, and subsequently the other processes or the other threads would not be able to proceed until that happens. So it goes into a hang that will never end. Okay. So in this case, we're facing what's called a deadlock, where all the elements of the system are stuck in one place and no progress can be made. So when you see that, you would then look at the program and what type of threads or processes are waiting for the resource, which is held by one another, which prevent other processes from executing. So it's like a relay process, in that I have to free up the resource for you to use, but you have to also free up the resource for me to use. So in that sense, it will be just stuck in one spot. So we would then define deadlocks as the conditions that concurrent program needs to have at the same time for all the deadlock to occur. And this is what we would specify as Kaufman conditions, who is the scientist that came up or discovered these type of conditions in a concurrent program. So these conditions would include mutual exclusion, in that at least one source must be in a non-shareable state, that it would hog all the resource. The resource would then be held by this process and cannot be accessed by the others. So in the case where we're talking about CPU, one of the thread or the process would then use the CPU where it would exclude the rest. Second, we have a hold and wait situation in that one process would is simultaneously accessing a resource that is being waited by another and is waiting another resource that is being held by another thread. So subsequently, we would have two resources that we would need to be able to execute. Let's just say we are holding one and we're waiting for another one that's being held by another resource. So it goes into a hold and wait stage. Third, we would have a no preemptive condition in that resource can only be released by a process or a thread voluntarily and actively release the resources that the resources remain in a non-shareable state. So if the other threads are not releasing the resources, it becomes non-shareable. So therefore, it would continue to wait for that particular release. Next, we would have a circular wait. And this is what we saw at the beginning. In that the first process of the set of processes is waiting for the resource to be released by the second. And in turn, the second is also being waited for the resource to be for the third. And the third is waiting for the first process to be releasing the resource. So it becomes a circular wait process in that the first waits for the second waits for the third comes back to the first because it's waiting for the first to be done in order for it to execute. So in the picture here, it shows that A is waiting for the resource 2, which is held by B, and B is waiting for the resource 1, which is held by A. So nothing can be achieved in that type of program, and we would have a deadlock. And so in that case, we would see the example in Python like this. So before we start answering or before we look at the example, let's take a look at your questions. So in the first question, it asks you, when does a deadlock occur in a concurrent program? And you can see that from the first page. How do you resolve a deadlock? So the deadlock occurs in a concurrent program when all the elements of the program require the same resources to complete tasks. As resources are not released from, I have a typo here, various elements, no task can be achieved and no progress is made in the program. So as I'm waiting for your resource and you're waiting for my resource, we cannot accomplish both of our tasks. And that's what happens in a deadlock. So in the prior chapter, we talked about using locks, right? Lock from the lock class. We would create a lock object. And in that lock object, we would then need to be able to incorporate the resources that we're using. So the resource could be shared memory, right, for threads, which contains the data. So when we create the lock object, we can link the locks to the resources. Then we would control the order of how that resource is accessed across the threads or the processes. Okay. Now, when we think about order, we would then question, would that become sequential if it then goes back to the order on how the locks would be released and how the resources would be accessed. And we would address that as we look at the example. So one of the solutions to really resolve a deadlock would be implementing lock objects and linking those lock objects to the resources. And resources could be CPU or shared memory. Then we would control the order of how the resources are being accessed by the threads or the processes. Okay. Any questions regarding deadlock? So concurrent programming is a way that we can improve performance, but sometimes you would find that implementing the solutions for such as parallel processing or multi-threading might not give us any kind of improvement in time, in that subsequently we would then revert back to how we would control our lock objects and the resources, which might even give us longer time to execute that program or equal to the sequential execution time. And since we have answer number 1, we will proceed to number 2. Number 2 asks you about Kaufman conditions in deadlocks. And the conditions are mutual exclusion, hold and wait, no preemptive condition, and circular wait. And you can find the details in the notes. So in mutual exclusion, we mentioned before that at least one resource is using a non-shareable resource state, that it's holding the resources and the resources cannot be accessed by others. Second, that will be hold and wait. And that means that one process is accessing the resource while waiting for another resource that's being held by another process. Then third is your no preemptive conditions. That means that the resources are not voluntarily released by other processes or thread, which makes the resource become a non-shareable, operates in non-shareable state. And then lastly is your circular wait. And this is just a waiting state for the resource to be released by the prior or the subsequent processes in a circular pattern. So the first is waiting for the second, it's waiting for the third. The third is then wait for the first. Yes. And when you look at resources available online for other languages, you would see the same for Java and other programming languages. Now, keep in mind that, of course, they use libraries that look similar to Python, right? We can implement parallel processing in Java. We can also implement parallel or multi-threads in Java and other languages. And you would see the same conditions that are carried, right, for deadlock in other languages. So as you design your project, you want to be mindful of how you would implement concurrent programming, right? In the aspect that, yes, certain type of processes can start other processes, or the program might go into deadlock. Okay. And then we'll talk about it too. Any questions with number 1 and 2? So for final exam, we want to know what a deadlock is and how to resolve a deadlock in general. Second, we want to know the conditions or Kaufman conditions or deadlock conditions and what would cause the deadlock. Okay. So I put the code in and I copy and paste it. So if you didn't download the code, you can run them by putting it into your IDE. So in the example 1, and in this, if you read, right, we have a function called thread A. And here we simply just print that it's starting and it's waiting for the lock and it's going to acquire the lock. Okay, remember that we use the lock and we simply use the threading module in this one as we use multi-thread. And we print that it has acquired the lock. And then we're going to make it do something, which is it's going to pause there. Then we're going to have thread B that's going to acquire the lock. I'm sorry, thread A that's going to acquire the lock for B. And as thread A is acquiring the lock for B, it's going to sleep or perform some kind of calculation so it can execute something there. We would then release the lock A and the lock B. So thread A would then release both of the locks. Then in thread B, we are doing the same thing here. We're going to print thread B is starting. It's going to wait to acquire lock B. And then it's going to compute. Then it's going to wait to acquire for lock A. And it's going to print and it's going to compute. We're going to print that it got the lock A. Then it's going to release both of the lock for thread B. Now here we simply have a lock object, lock A and lock B. We are defining that as a lock object, so threading that lock. And then we have the thread object, thread 1 and thread 2. And our target, we simply use the function, right? A for thread A and B for thread B. Just like what we've learned before, we are going to start and join. And then we would print finish. So when we execute this, you would see that it shows subsequently, right? Thread A is starting. It's waiting for lock A. It got lock A. It's computing now, which it goes into a sleep mode. Thread B is starting. It's waiting for lock B. It got lock B. But wait, B got lock B and A got lock A. So A is waiting for B, lock B, and then lock B is waiting for lock A. So it goes into an indefinitely wait state at this point. You see? So none of them are releasing, but in the program, we have programmed it to be released after it's done. Well, one is not done with one of the resource and the other one is the same. So, and they were waiting on each other. So it now becomes an infinite wait. So as you can see, it will never get to the print line here at the end. As we tell it to wait here, right? As we do a join method, once it's started. So it has to wait for one to be finished, right? The other one to be finished in order to complete its task And so therefore it never completes. So we have no progress after that point. Question. So that shows example 1, right, on how what a deadlock would look like. And here provided the procedure, right, for our program, which was implemented in the algorithm. And this gives you a diagram of how the thread would look like when it's waiting for the lock. So as each thread acquired its own lock, it needs to access the other one, right? A needs to access B and B needs to access A, and that was never released. So it becomes a deadlock. So instead of using the resource arbitrarily, we can think about how we can put them in order. We can statically or sequentially set them up so that way they would operate in order. And so the way that we can acquire and wait for the resources would then be eliminated. So let's look at the program. Example 2. Let's clear this, pull this down. So similar to the other one, we have pretty much the same function. It's going to acquire lock A for A, and then it's going to compute, acquire lock B for A, and then it's going to compute, and then release. And then the second function, thread B, is the same. B is going to acquire, is going to start. But instead of waiting for, it's going to wait to acquire lock A, but instead of obtaining lock B first, we can make it obtaining lock A and perform the calculations. That way, B would then be available for lock A to use, right? And then thread B would then acquire lock B. So the order of that has been changed, because before we would do A to A and and then A to B as a second step, which we kept. But for the second function for B, we would then have it obtain A because A was released and freeing up lock B. So then the A would then be able to use B and then release that and be able to. So we just changed the order of that. Okay. So subsequently, we would then release B and then A. And so again, we would define the lock objects and the thread objects, and we would keep start and join the same and print finish. So as you can see, it does take a little bit and it's able to finish, but it does take a little bit longer than a what you would see would if it just goes sequentially. So we would see thread A starting, wait to acquire lock A. It got lock A, it computes. Then B is then going to the wait. So it's going to QB to acquire lock A as soon as, and then A is going to wait for B. So as A completes, okay, it's going to release both the locks. Then B is going to obtain lock A, compute, wait for B, got lock B, compute, release both lock. And this one, it does finish. So we simply change up the order a little bit and we achieved program completion. Okay. But what happens in that solution is that it's still quite inefficient. Right? So to really fix some of the deadlock issues is you need to really map out what kind of resource that you're using with a certain task. And then when that task is accessing that resource, if it's a shared resource in the case of multi-thread, and how it's releasing. And if we can change up the order in that when a certain resource is released, then it's going to be able to access by the other processes. Otherwise, you have a process or a thread that's using all the resources, then you would run into starvation issues, which we talk about next. Okay, so this program shows how, going back to the example with the 5 philosophers, on how we would be able to coordinate, right, the fork, the left and the right fork on picking up, and be able to do that. So what they're saying here is that if we start tracking or counting, right, the way the order of the forks is being used, and when you put it into a for loop that allows it to be able to count, right, we can set up a count for that, and we would be able to set up where the philosophers would then be eat and think and put down the fork subsequently. So I'm going to show the next one, and then we got to move on to the next topic. So let's look at example 4. So I'm going to clear this. So in this program, this is another solution to it, and it is a little bit more elevated. And this is a way that we can elevate the 5 philosophers program, right? So what you see here is we have a class called acquire, and we would have the locks. It's gonna then create a dictionary for the lock. Then we have a loop, and in the function enter, right, we would have a loop where we would be able to use that loop to acquire each of the lock for the 5 philosophers. Then we would be able to release using the exit function. So it would then use another for loop, and we would unlock it basically. So we would then release the lock. And outside of that class, we would have a function called philosopher. And in this, we would have a while statement. While true, we use with statement with acquire, with left and right, we will print that they are eating because they need both forks to be able to eat. Then we also define the number of forks, which is 5, which allows us to control the loop. And our forks object would then represents our thread. So we would then need to associate that with each time that it loops. So we are going to loop 5 times, of course, and it's going to lock it 5 times. Now we have a list called fills that's going to contain philosophers, and these are our workers, which are our threads. And the target is going to be the philosopher function, of course, because we have to loop for them to eat. And so in the last part, we simply is going to start the threads, and that would enter at them and then be able to call these functions. Okay. So on this one, what you would see is that you would have okay. They would be eating. Let me pause it. So you would have various threads. So you would see that thread 4 is started, and then that will be eating. And then we would have thread 5 would enter. And then also 1 and 3. So as you would see that we do have a concurrent program that is working. And then some of the thread will be eating first, right? So that will be able to achieve first. And what it would do is it's gonna queue the other threads, thread 1 and thread 3. And then eventually after 4 release the resource, then 1 would then eat, and then 3 would then eat, and then 2 would then eat, and then 2 release the resource, then 4 would then be eating, and so on. And this is infinitely running, so it just keep on going and going as we have the while true. Okay, so that's an example of what deadlocks would look like and how to resolve a deadlock using counters and how to order them. Okay. So at the end of the chapter, it talks about a Livelock. Most of the content is like your code, so okay. So if you look at page 13, oh, before that, I want to mention this, it's important. Okay, so the important note is that locks don't really do anything, right? It's not like preventing things from entering or whatnot. They're simply just flags that indicate the resources are being accessed at any time. So when we construct a program, we really have to think about how the threads are accessing the resources. Okay, even if the locks exist. And we have to think about how locks are associated with the resources, because they might not always be connected to the resources, which do not allow them to block other threads. Okay. So to effectively use the lock, we want to make sure that we use the lock object. We associate that lock object with either the type of resource, the shared memory that we created. Okay. Now, to use the lock effectively, we should also think about implementing secure dynamic concurrent data structure, like using a queue, which link the locks between the locks and the resources, and utilize synchronization tools. Then following that talks about Livelock, which is a situation in that a request for exclusive lock is denied repeatedly because there's overlapping or shared lock interfering. So if you have the allowed processes that's defined by a certain number of entries in the process table, that can cause a live lock if they are overlapping. It's like when you're walking down the hallway, and to avoid another person that's also walking the opposite direction, you're both moving to the left, which still prevent each other from passing, or moving to the right together, which prevent you from passing. So in this, because they are overlapping, they are interfering with one another as they're sharing the locks or the resources. So it also prevent the program from proceeding. Okay. So to answer the next question, we can say that Livelock is a situation where a request for an exclusive block is denied repeatedly, as many overlapping share locks keep on interfering with one another. And you can refer to page 13. So the second part of the question, it asks you, how do you overcome a live block? Right? That's why we're learning. The concept is to really think about how we're going to be able to overcome these problems when we come across it. So after the example of the live block, oh, it goes into starvation. But what we need to think about is how we would be able to control what process is being overlapped for what resources. So if we have coordination in that, and we need to manually or statically set that up. So if in the case where you and I are facing each other down the hallway, and I would tell you, you move left and I move right, that would allow us to bypass each other, right? So then we would need to coordinate the process, so that way subsequently they would be able to access the same shared resources, even if they're overlapping. Because when we're doing concurrent programming, we want to overlap and we want to set them up as queue, right? They all start together. But as they execute, going back to Michelle's question a couple weeks ago, we would then set up some subsequential process in that 1 and 3, right? 1 would go first, and halfway through, 3 would be executed, and then halfway through 3, and so on. So we do have to have some sequential coordination in how the resources are being utilized as shared. Okay, so we can add that. And that's how we can overcome Livelock. Okay. So in the deadlock, right, we've learned about how our threads can hold up resources and can cause the program to stop running. In the second part, the next chapter, it goes into starvation. And I think you heard about this before, also with race conditions in the prior chapter. So starvation is in that the in a situation where low priority processes got blocked from because the high priority processes already proceed and use all the resources, or occupying the resources, I should say. It's kind of like how you would have a parent that have two kids, a favorite kid and the other one is not as likable. The favorite kid would then be able to get all the attention from the parents, and the second child does not. So the second child can never get their request fulfilled. So in this case, that the high priority process or thread will always be able to utilize the shared resources and execute. And the lower processes, the low priority processes will never be able to achieve that, because as it executes, right, for the high processes, it's going to keep going and keep going and keep going. And the low process priority processes will never be able to get its request fulfilled. So, and in the design of the program, we would see that one process is responsible for handling extremely pressing instructions. So it's always going to need to run as soon as the resources become available. So it's hogging all the resources. And it's going to starve out the other process, which is not as essential. So the example here is that we have three processes. One is pressing, the other one is not as pressing. So the one is pressing is going to be running. Then the second one is going to go into queue, and then so on. So back and forth between the two, the third one would then just handle the miscellaneous task, which never gets completed. So normally it tells us here that we would implement priority execution to access the resources for the first process, then the second process, then the last process, but that becomes a sequential program. So if the resources are being used with the first process, the third process is not given any opportunity to execute. So here is where we need to consider scheduling and coordination once again. So we would then need to coordinate the tasks, and we would think about how we can effectively schedule the task so it doesn't cause starvation. And a way that we can approach this is to do task switching, in that the CPU is not starved in the execution flow. So if we distribute the execution flow and allocate resources equally, then there will not be starvation. So a way that we can implement order scheduling is what's called priority inversion. That we want it to lead to the low processes. So it's like having a parent answer the priority, the favorite child's need, and then switch over to the less favorite and answer their needs, and then switch back and forth. So we have to release the resource, the parent, to the other less priority processes, right? Common sense, but it's sometimes would be harder to achieve where you have certain things that need to be executed first in the program and it never gets done. Okay, so then We can answer the next question. What are the causes for the starvation? How can you resolve starvation in the concurrent program? So the causes are processes and threads with high priority dominate execution flow in the CPU, and the low priority process thread is not given the opportunity to execute instructions. Second, the processes thread with high priority dominate the usage of non-shareable resources, preventing the low priority processes from executing instructions. Third, processes threads with low priority are waiting for the resources indefinitely or infinitely because the high priority processes threads are occupying all the resources. Like what I said about the favorite child keeps asking for the parent's attention, it never frees up the parent for the second child. So with those conditions or the causes, we would say that starvation can be resolved using algorithm scheduling, using queues to store and update threads in waiting, along with queues for shared resources. So we need to have data structure implemented for threads. And it's always going to be changing in that data structure, right? So it needs to update the status of each of the thread as it's being handled by the CPU. And also we would have a data structure, which is the queue for our shared resources, because as the other threads are using the shared resources, it should also update that container. And that would effectively allow us to use the algorithm scheduling technique. Otherwise, even if we schedule it, it will become more of a sequential process versus a concurrent process. So strive for balance is the ultimate lesson here, right? When we switch tasks, we really want to balance out the low priority threads or processes with the high priority threads and processes. And as developer, you have to achieve that. Questions? So in the scheduling section, it talks about priority inversions, right? Where we would see that low is going to also take the flag, and then the medium is it's going to give the flag at 1.2 the priority, so the priority would then be able to execute. So here it kind of map out a diagram on how you would be able to implement priority inversion. And the key in this is when we combining the priority inversion and starvation, it can lead to where that high priority tasks are unable to execute instructions because the other ones are taking over the resources. So it becomes it goes into a starvation, but for the reverse condition. Okay. And the causes for starvation, you can find it on page 15 and 16. So a good example for this is where you would have a program for read and write, and we've seen this previously. Let's say that we create a thread for the reader and a thread for the writer. Now, we can, after we write is when we'll be able to read the file, right? So for example, like a receipt, when you, after you process your transactions, in that you would record that transaction. So you have to write that transaction and then execute the read, where you would be able to read the receipt and display the information to the customer. Now, in order to really build out the program, we can say that reader and writer cannot access the shared resources simultaneously, right? You have to write the data in order to read. Now, if we write, then the thread for the read would not be able to access it. So it has to wait for the writing process to be done in order to read. But to achieve concurrent, we can say that what if we have more than one reader thread? What if it's a pool? And what if we have a writer thread pool? Okay, and we are using that shared data space. So we gotta make sure that we're not corrupting the data at the same time. Okay, we know that the readers don't change anything in the data. So why can't we make that first? Okay, and the writers, it would require both read and write. So the first solution would be that lock the text file to make it non-shareable, allowing one thread to access the file at a time. But that becomes sequential if we're not overlapping. So we have to go with the solution in that we would have multiple readers that can use the file simultaneously, but because they don't alter the data, no readers are then be kept waiting for that shared data. Then we can implement the counter to control the number of readers and the lock resources for, and we also need to implement the counter for the lock resources for the writer. So as we loop through, we would then count down to 0 as we decrease down to 0. The lock would then increase, so that way after we read for each one, we can write to. Okay, so it would decrease on the read and increase on the write. And so if the first reader would then need to place the lock on the resource, the subsequent readers would have to relock until the last reader is finished. And when we approach it using this model, we would say that this becomes the reader preference, where we prioritize the readers over the writer, which might not be desirable, but in a certain type of scenario, like what we talked about with the VC, we won't have any data until we write the transaction. So if we're just reading and updating the file as we read, that this model would work. But in order to have the data to read, we would first have to write. Okay, so it might not be desirable for all circumstances. That's what it's saying. And this is how you would implement the writer and the reader solutions. So let's take a look at number 2. Let me clear this. Okay, so this we're also using multi-threading. So threading module is imported. We have a function called writer, and it uses 2 global variables, text and W count for word count. and simply that we are finding a solution to read and write a file in general, right? We have a while loop, and here we would implement the counter. So with, right, W counter, we would increment, so we would count up. If it is 1, then we would acquire the lock, retry. And then for the resource, we would print that writing being done by and the threads information. For the text, we would then have it is the increment of, right, the object. So then the writing would then be done by. So this is a way that we can display it to the user. And as we count down on the word is counted down, we would then release. How we talked about how when it reads, when it gradually gets down to 0, we would then release the lock for the resources so that way it can write. In the reader function, we have our count as a global variable. We have a while loop. And here we would increment the R counter for our count as it increment up. If it is 1, then we would acquire the lock. And we will print information about that thread. And as the counter is reducing down each one, and when it gets to 0, we would release. Our text is going to be, this is some text. Our variables are initialized at 0. Then we have lock objects, W counter, R counter, resource, and retry. Here is our thread pool, right? Our target is going to be reader because we talked about how we would set up the readers first. And we would loop using a for loop. So 3 readers. Then we also going to have the workers for writers, and that will be 2. And we would start them. And so this one is going to also go for a while, right? So let's stop. So we can see the output, right? It's able to read, this is some text, this is some text, and so on. So it's always gonna be with the thread 1, where what happens here is that when you add in the read and you count down the read, it's gonna rejoin. So it's all because it's reading, the readers becomes the preference. So it's always gonna read, as you can see there. Okay. So implementing a solution like this, the file is only read, but we don't see that it's writing, right? It shows that thread 1, it's just going to read to us, this is some text, and that's it. So when can we fix it so that way the writer's thread can be executed? Let's clear this. So similar to the other one, right? You also have the writer functions, the reader functions, like what you have. Okay. But in this one, we are going to only use our count. So as we increment on the reading side, we do the reader. If reader is 1, we would acquire the lock and then we would release it. If the counter is reducing down by each one, then when it gets to 0, it's going to release. So as it use the resource, you need to make sure that it's released. And notice that this is the counter, right? And then this is the resource. And they're 2 different lock objects. And then you have what's called a service lock. So we do have the pull thread like what we have before, and we would start the thread. But here is in the writer is where we would implement the service lock. We would acquire that and be able to get it to execute. So it's a slight change in the program. So when you run this, you would find that, I'm going to pause it so you can see that we do have writing and reading being done. So we have thread 5 and 4, which is writing, and then thread 1 and 2, right? And then thread 3 and 5. So you have writing being done, release, then reading being done, and then release, right? And then some writing being done and release, and so on. So if we add in the writer's preference, like what you've seen in the example 3, we would then be able to implement for both readers and writers, and we would then need to set the priority to be equal because you want to be able to achieve reading and writing for the file. So each reader and writer obtain the block before the execution and releasing them immediately. And that what is shown in example 3. Okay. And that's if we simply just want to read and write the file. There's no higher in priority. In the case of higher priority, like you have to write the file in order to read, you have to think about how you would be able to achieve that without having starvation. Okay, like what we talked about in the last example where it would be one side more than the other. So the solution for the starvation is that you need to think about how you can increase the priority of the low priority threads. So that way they can be squeezed in with the high priority threads throughout the program, not wait forever, right? And you want to use first in, first out thread queue to store thread requesting access. Also, we want to use priority queue to gradually increase the priority threads that are waiting, sharing resources, and have less priority. So what we're seeing in the prior concept and this concept is that we have to implement data structure to really strive for a better balance in concurrent programming. In that, in starvation, we want to use thread queue to store the requesting thread access information as it updates it throughout the program. And the queue gives us the flexibility in changing, right, content and size. Second, we want to also think about how we can increase the low priority threads and put them onto a queue and update their status in waiting and sharing resources. So that way they can take part in the program instead of waiting forever. So you will find the solutions information on page 21 of our notes. Any questions with starvation? All right. Next chapter is chapter 21, which is on race conditions. And in race conditions, the output is dependent on scheduling an algorithm or the order of the task that's executed. So when you have mishandled data or corrupted data, it becomes a problem. And this can happen in hardware or software. Okay. So we learned when we talked about parallel processing and multi-threading in that multi-threads, a lot of the time, if we create a shared location of data, right, one thread can change the data and the other thread would use it and it becomes then corrupted. And the area of the data is called critical sections, which is a protected area for your critical data of resources. If they are altered, then the data becomes corrupted and it would be poorly handled in the coordinating or the scheduling. So we can think about how we would disallow multiple agents in accessing the critical conditions at the same time. And this is known as mutual exclusion. So as we looked at the last example, we saw the read and write processes. If you gradually increase the priority, don't they just become a high priority thread? So then, yes, so they would be equal in priority. And that's what we've seen in the example, Michelle. So then if you elevate the level for the priority of the threads in starvation, then they are not just waiting for all the high priority to become available, right? So it would then be able to switch back and forth. Now, if we are able to achieve that for the program objectives, but in the case that we're not, right, we would then think about whether concurrency is really a solution in the program. Sometimes we would revert back to sequential approach and be able to strive for the program objective, your program goal. So here we can see is that when there is an edit, right, we can have the read and write. So task 2 gets to update from task 1. So task 2 is here. Task 1 is going to update it as it shares the data. And then task 2 is going to read and it's going to write. So as we access the shared data concurrently, we would then read and write. So in the subsequent task, it's going to get the updated value from task 1. Now the incorrect behavior would be that task 1 read, task 2 read it, task 1 write, and then task 2 would then write it. Okay. So task 1 and task 2 work on the same data, where if it would not be appropriate. So for the next question, we can describe race condition as a phenomenon that the output is dependent on the scheduling algorithm and the order of the task executed, because the data might be affected. We can think about how we would use mutual exclusion to protect the critical sections where the data could be updated or corrupted. Okay, let's not answer number 6 yet. Talk about that. So here we can see that, let's take a look at the program. We can pause the execution in the function, and we can implement counter to control the processes that are sharing the resources, right? An asset loop, is sequentially calling the target or using the target function. So I'm going to go to second example. Let me clear this. Let's look at the first one first and compare. So here we have an example. We're going to use random threading and time. We have a function called update. We have a counter variable. And we're going to use the counter to track our reading shared resources. And we want to simulate some kind of calculation by doing the sleep with the random int method. And then we want to update the shared counter by adding 1. So we initialize counter as 0. We have a thread pool, which contain our workers, and our workers are going to be 20, right? We're going to loop it, and our target function is update. We're going to start the thread and join the thread, and we need to put them in separate for loop. We talked about this before. We want to print the final counter and the finished. Okay. So our final counter is actually only 14, and it's completed. Now compare that to the second example. Notice that this one does not have a lock, right? In the first example. And in the second example, we also have a global counter, but in this time, we're going to implement the lock. So with count lock, we are going to create, that's a lock object. And mostly we would have the same thing down, right? We start the thread, we join the thread, we output. But in this one, we added a lock. Okay. And with this, it did complete all 20 versus 14, not what we seen earlier. So we did finish. The other one stopped early, right? You saw that it only executed 14. So now we're able to get 20 and finish. But if you time that, right, if you actually put the time to be output, you do see that it took a little longer than the prior program. So for a well-designed program, we would successfully increment the shared counter and update the shared data just in time for the next thread. We would use locks, which are associated with the critical conditions that are used. And the locks would be used to protect the critical condition to prevent race condition in that one thread would update for the other threads. And once the lock is released, then the thread would then leave the critical condition. So the lock is used to really associate that thread to a certain part of the critical condition. And with that, we would say that it needs to be associated with the resources and other threads can gain, otherwise the other thread will be able to change or corrupt the data. And the other program components must be interacting with the lock to protect the shared resources. Okay. So in the second solution, you would see that we implement the lock, but not only that, that lock is really associated to the resources that's used for that specific thread. And it to prevent the other threads from changing the data in the critical sections. So going back to what we talked about deadlock and things like that before, the lock doesn't really lock anything, right? It's just a way that we use that lock mechanism to update statuses or using flags in the program to make sure that we track the status of our threads. Okay. So a diagram of it would be something like this, right? The way that we see in the example program that you would have a mutual exclusion variable that would represent another container, which is the variable. So you would then have a container in the container to really associate what specific part of the critical conditions that would represent or that will be used for a specific thread. Now, race condition is very important. This generates a lot of security issues for hardware and software. In authentications, if the data is corrupted with the credentials, it can cause privilege escalation or gaining access to something that would be unauthorized. So to think about from an attacker standpoint is that they would test a certain application and see how, if it is a concurrent program, right, we would see how that can eventually result in race condition in that we would be able to gain access or escalate the privilege, because that would be the step once they got into the system, right? To gain access and then escalate privilege. So from a developer standpoint, we want to eliminate race condition in such case, and it would stem from having checking credential, because the time to check is when agents would check the credential that would then need to update the authorization part, which is then the time of use. So if you have a data corruption between these two processes, it will cause access issues in security for that application. So we can say that race condition can occur in authentication, where data is corrupted between time of check and time of use, which could cause, right, unauthorized access and privilege escalation. And privilege escalation is just a phrase to refer to somebody that have higher privilege than they should have, right? I can enter as a user, but I have administrator privilege after. So we want to thoroughly test and make sure that we handle race conditions to prevent security issues in the application, such as privilege escalation and gaining access. And in the prior chapters, it talks about how race conditions can occur, and we would be able to use GIL, which we will revisit that in the lab for this week. Okay. We only have a few questions today, so as they are all mostly concept. How can one core be faster than another core in concurrency? Is the manufacturing aspect or is a computer aspect? It would be assumed that the cores are made and designed the same way. Yes, you are correct. The cores are made and designed the same way, but we do have the capability to be able to allocate certain type of resources to specific core. In that, if you ever use manufacturer software, right, AMD or Intel, you can specify, right, the threads and the things that can be allocated to us, what we would see as a logical core for our processor. So in simulation of that, VirtualBox doesn't allow you to do that on a virtual machine level. However, if you setting up your core, you would then use the manufacturer applications to be able to tell the system, or but architecture wise, they are made to be equal, and they are designed to. And you can also, like how we would be able to set up 4 core functioning out of the other 4, right, out of 8. So you would have 4 are going to be taking priority versus the other 4, we might be able to mute them or silence them. So in that same aspect, we would be able to have the priority in 2 cores versus the other 3 and so on. So not all tasks need to be executed by all cores, and not all tasks can be prioritized as equal, right? In some cases. And we would see that it might cause the conditions that we talked about today. So we have to intelligently think about how we would resolve the issues. But really focus on addressing the objective or the goals of your program altogether. Okay. And if you are ever want to learn a little bit more about like the resources for the CPU, you can use software like CPU-Z, or if you have like AMD software or Intel software to turbo boost your system. Usually there's a tab on there that you will be able to look at how you can configure, right, each of the core and how many cores you want to use at a certain period of time. They all come with that, but there are third-party software like CPU-Z that would allow you to look at the number of threads that's allocated to the core and so on. Okay. All right. Are there any other questions? So I would say the next chapter, which talks about the GIL, right? The module, we'll do that for the lab. So you have more of the hands-on application with it. Going back to multi-thread and parallel processing. And then if you want to pre-read during the Veterans Holiday or something later this weekend, we can read the patterns, which is going to be the last part of the text. Okay, we're going to group them together and attack them all at once. Okay, no questions? Okay, I'm going to stop recording.